Previously, you have looked at the circular motion, how things move in a circle, what's the centripetal force, and things like that. Now we move on to applying those ideas. Now, this chapter 8 is very exciting because there's a very recent discovery called gravitational waves that happen. Oh, but before we understand that, we need to know the basics first, okay? So, just for this video, we're going to look at what is a gravitational field. It sounds familiar, but then again, at the same time, it's like not quite familiar. Like, what is this? So we're gonna learn by the end of the video. Make sure you know what is the gravitational field, how does force and this field relate. Then we're gonna look at this kind of new thing called Newton's law of gravitation. Ooh, sounds so funny, so cool. Newton's law of gravitation. Okay, so first things first. Fields. Do you remember fields? What are fields? Okay, we've seen that before in AS. If you want to say what is a field in general, you can say that it's a region of space where a body or some object with some properties experience a force. What properties? Well, you have like what we call electric fields. So in electric fields, your charge is the object. The property is like, I guess, a charge, coulomb. Okay, so if you have a charge in the electric field, then yeah, it's going to move around because there's a force, electric force acting on it. Then also we've seen before in chapter 5 and as well as chapter 6, if this is, let's say, the ground, this is earth, ground. If you put a box way up here, you let go, it's going to go down. Why it goes down? Because there is what we call the weight, or what we call the gravitational force. Ooh. And this gravitational force is acting on this box. Why? Because you're in a field. So you look at these two ideas, this field, these lines, these arrows are the fields, field. So that's what it means, field. But now, we're going to zoom in a little bit more on just the gravitational part. The electric part, we'll save it for another chapter completely. So gravitational field, very specifically for gravitational field only, you can say it's a space where a mass experiences a gravitational force. This mass is a property of your object. Okay, so like previously, I drew this thing lah. This is what we're more used to. You put a ball here, the ball will go down. Why I got weight? Weight is called a gravitational force. This one, Fg. And this is the earth law, the ground. But if you zoom out a bit, you will see this whole earth here. And actually, you will have a gravitational field, something like that, pointing to the center of the earth. You say, Miss, that looks like a point charge. Yeah, it's the same thing, lor. Except that you can only attract, cannot repel. So, any kind of object, if you put a mass here, test mass, see this small little dot here, it will experience a force towards the center of the earth. That's a gravitational field. But what is this gravitational force, this Fg? Let's do a thought experiment and try to follow in the footsteps of Newton to come up with this law of gravitation. Okay, just now I said there's two objects, right? Okay, let's rewind and break it down. Because that one, if you just memorize definition, you won't understand. So let's go through the explanation of it. Let's say I have two objects here, two spheres. You can see here, one is big, one is small. The first sphere has some mass m1. Which is bigger lah. The second sphere has some mass m2. Okay, this is the center of the sphere. Okay. Now, just by having mass, it will attract each other. Imagine you and someone you really like floating in space. Eventually, you will have attractive force to each other and you will like, eventually you'll stick together. Why is that? Because you have mass, you have force. What does that mean? Okay, so these two are here. They are at some separation apart, okay, from the center here. We use radius r as the separation distance. Okay, and now here comes the fun part. This first mass on the left side here will exert a force on the one on the right. So, kind of like this. This is the force of number 1 on number 2. Okay, that is the big one pulling the small one. Also, the small one will also pull the big one towards itself. And that is something like this. This is the force of number 2 pulling on number 1. Two forces. So they attract each other. I attract you, you attract me. They go together like that. Okay, so that is Newton's law of gravitation. But we need to come up with an equation, right? Because physics, equations. But before that, let's write out some facts about these things here. The first fact, fact number 1. Yeah, I'll use blue color. You see these two red arrows, right? This looks familiar. F2 on 1, F1 on 2. Where have we seen this before? This is in AS, called Newton's third law pairs. So you can say the first fact, both F21, I lazy to write the on lah. F21 and F12 are Newton's third law pair, or what we call the action-reaction forces. Action-reaction pair. Same type, equal magnitude, opposite direction. Same type, equal magnitude, opposite direction, acting on different bodies. Okay, pass. So these two are the red ones. That's the first fact. The second fact, what else do we know about this thing before we construct our equation? Do you think this thing can repel? No, it's attracting. M1, M2 attract. So that's actually true. For all kinds of gravitational forces, you can only attract. So, I summarize here. F21 and F12 are always attractive. Means there's no repellation. Is that a word? Very attractive. Wow. Woo-woo. Okay, how you know attractive? Because the arrow point to each other. I pull you, you pull me. Okay, so that's two facts that we know. Now the third one is where we will come up with the law of gravitation. To do that, I'm going to open up a simulation for us to have a look at that to come up with the idea. Okay, then here, you see they redraw a moon and an earth. Oh, very nice. They also give us the chance to change the size of the planet, size of the moon, and distance of the separation. How far are they apart? And you see down here, right, there's Fg and Fg. That's the gravitational force. Okay, so the goal is, what variables affect the gravitational force? Okay, how do you know that? You look at the arrow, the size of the arrow, the blue and the red. If they're very far apart, look at the arrow, very small. See? But if you put them closer, the distance of separation is closer. Oh, look at that. The arrow becomes so big. That gives me an idea that the force is related to this separation somehow. When the separation is big, force is small. Okay, so keep in mind, separation is a factor there. Then you have the mass of the moon and mass of the planet. Let's say I make the moon mass very, very, very high. Wow, you see the arrow become big. Okay, so something about the mass of the moon affects this gravitational force between these two. And the planet also, if you can change that, that also changes. So you got mass of this first planet, mass of that second planet, and you have the distance separation. How do we tie them all together in an equation? So Newton sat down, thought about it. He said, all right, we got mass as a factor, both masses, and R. So he did some experiments, some thought processes, and he came to the conclusion that the gravitational force, F21 or F12, either one, is proportional to the masses and their separation distance. Okay, M1 is the mass of the first, M2 mass of second. And that's what the sentence we saw just now is talking about. If we translate that equation, the relationship that we saw just now, into an English sentence like this one here, then we get our A-levels definition. This one you must remember. Okay, so the attractive force, gravitational is attractive force, gravitational force, between 2 point masses, okay, the two stuff we look at, is directly proportional to the product of the two masses, well, M1, M2, and inversely, it is directly inversely proportional to the square of separation. That's the whole definition. The full one, Mark schemes you see sometimes may be a little bit different. They may only include 2 points out of this, but the fullest one you can write is this one above. Alright, so make sure you keep that in mind, how to remember that. Anyway, so we got that relationship already. If we turn it into an equation, we can use it to calculate forces between two masses. Now, if we change a proportional relationship to an equal equation, then you must include a constant. So people did experiments and they found a constant G. M1, M2, two masses over R squared, their separation. This one is the equation that we'll be using to calculate stuff and all kinds of other stuff. Well, anyway, so what is the unit of this thing? You don't panic, you see so many things. It's still force. So your unit is still Newton. And of course, a force is a vector. Force this way, force that way, force up, force down. Okay, all kinds of stuff. Now, let me just recap a little bit to remind you what this G is. We call it the gravitational constant. You can find this in your every exam paper at the beginning, got a long list of constants. It's in there. And the value is a very, very small value, 6.67 times 10 negative 11. And the units, we calculate the units from the force, the mass, and the R, and we will get Newton meter square kg minus 2. That is the constant. You can also find it in the calculator if you know how to find the constant of G inside here. One last thing I would like to highlight to you is the word they use, point masses. Why they say point masses? Obviously, it's like Earth, Moon, it's round-shaped sphere. But why they call it a point? That's from this idea right here. If your sphere, give me a second. If your sphere has uniformly distributed mass, so you say the mass is spread evenly throughout the whole sphere, then you can say it behaves as a point mass. So, okay, it's 1 point mass like that, concentrated at the center, all the mass concentrated at the center. So that's why, although the Earth and the Moon is like a circle, we just look at the point and we say, what's the difference between them? Point mass. Okay? So remember this definition, that is Newton's law of gravitation.
Okay, welcome to me again. I'm here to talk you through a few examples. All right, specifically when regards to Newton's law of gravitation. So you understand from Miss Ellie that whenever you have two masses, they will attract each other. Okay, so I want to direct you to this question, ON 16 paper 4.1. Okay, and if you are looking for the page number, this would be
of gravitation.
Page 15. Okay, so in this question, right, you have a satellite in a circular orbit. Okay, and as you can tell, right, because it's a circular orbit, the satellite will experience an attractive force towards the Earth. Of course, the Earth will also be attracted to the satellite, but right now, we are only concerned about the satellite. Okay, so because there's a circular orbit, somebody needs to provide the centripetal force, and the somebody here is gravitation. So gravitational force provides the necessary force. So you are asked to show that the period of orbit is given by this expression. So in A2, right, whenever you encounter paper 4 question, always now it can be a bit complicated, where they ask you to derive or show a relationship. But if you fall back into the main concept, you should be fine. So there are many hints inside the question. Number 1, circular orbit. So gravitational force provides the centripetal force. Okay, so it's always attracting the satellite towards the Earth. Okay, and when you ask to show the period, I would think about using omega. Because if you remember your centripetal force equation, mr omega square, omega here can be calculated or written as 2 pi over t. All right, let's continue. Okay, so now putting all of this together, I think I can start with that concept. Now, sometimes they ask you to explain your working. That would be the explanation. No? Gravitational force provides necessary centripetal force. Okay, so please do not skip the step. Do not jump something important. Always start by FC is equal to FG, because that is where the first mark lie. You don't get the first mark, the subsequent marks you might not get. Okay, so Fc is mr omega square, Fg is gmm over r square from Newton's law. So the first order of business is to cancel off the mass. Okay, so the mass I'm cancelling off is the mass of the satellite, because here you have the satellite moving in a circle, and gmm, this will be the product of the masses between the satellite. Small m is satellite, big M is Earth. Okay, so I'm going to cancel off the m, and I'm left with this expression, gm over r cube. So omega square is gm over r cube. I can substitute omega as 2 pi over t. All right, substituting as 2 pi over t, I can rearrange now. Okay, so 4 pi square r cube over gm will be equal to t square. So proven. All right, next part. A satellite in geostationary orbit appears to remain above the same point and has a period of 24 hours. State two other features of a geostationary orbit. So when it comes to geostationary orbit, right, we are talking about something that is stationary with respect to the Earth observer. Geostationary, stationary to ground. So number one, it must travel on an equatorial orbit. Number two, it has to travel from east to west, because the Earth is rotate. The sun rises from east to west. So the Earth must travel from west to east, must rotate. Okay, if not, you cannot have the sun rising from the east lah. Okay, so in this part, right, we will talk more about geostationary satellite at the very end of your syllabus again in communication. But today here, there are three properties of a geostationary satellite that they sometimes ask in question 1 of your paper 4 lah, your first question ma. Okay, so period of 24 hours, because it has to turn together with the Earth. So if let's say, right, let me find something. Let's say this cup is Earth and purple pen is a satellite. If they are going to turn together, this one will rotate. It will rotate at the same orbital speed. Does that make sense? So whenever, right, okay, I'm just going to pan the camera down a bit. So when you see this cup, and okay, I'm going to use the spoon. So let's say you have a human standing on the handle, and when the cup rotates, the spoon will have to rotate together, so that from the perspective of a tiny human being on the handle of the cup, the spoon is always at the same place. And this is very useful for communication satellite. You don't want later the Earth turn halfway and then your maxis no coverage. Very sad, right? Okay, so basically, if the Earth rotates at 24 hours, one round, the satellite also must be 24 hours, one round. And it has to be along the equator of the Earth. Okay, so it can, the equator is not the geographical equator. Anywhere can be the equator. Think about the sphere, okay? The thickest part would be the equator. All right, so, and it has to travel from west to east, because the sun rises from east to west. So the Earth is rotating from west to east. Go and think about it, or come and talk to your teachers. We shall continue now. All right, so the next part, even if you cannot prove the equation in front, you can still use it here, so please use it here. You are given the mass of the Earth. Use the expression to determine the radius of a geostationary orbit. So just substitute lor. But when you substitute, you have to be very careful, okay? Oftentimes, right, students forget to convert the units. Whenever you have a gravitational constant or any kind of physical constant in your equation, you must convert to SI, because the gravitational constant 6.67 times 10 to the power negative 11 is the VVIP. Okay, so we're going to sub that in. That's why the period have to multiply by 3600, converting 24 hours to seconds. And after that, I can press my calculator just by putting values in. Be very careful about the prefixes. Normally, when it comes to gravitations, the values will be very, very big. So always make sure your answers are very, very big. Because if they're not very, very big, means something is wrong lah. Either you are wrong or something is wrong. Okay? So I'm gonna fast forward a bit. You can see, right? This is where I know something is wrong. So this is how we can tell, because the value is too small. All right. This is only about 900 km, you see. So at this point, right, on purpose, I'm showing you common mistakes for students. They will put down this value and they won't think again. It's a common mistake from the examiner's report, right? That students do not think about whether the value makes sense or not. Like for example, this is just 900 km. 900 km is it's not that big lah. All right. So this is because I've forgotten to inherit the square. You can see, supposed to have a square. So the square is supposed to follow the t. I've seen this so many times. Every year when I set a question, people forget the square. Okay, so when you include the square, and now you'll be able to get a more reasonable answer. All right. Because the Earth's radius is 10 to the power of 6 already. Yeah. So I don't know what kind of satellite can be like that. Anyway, gravitational GPS system. Okay. You now have what we call a satellite orbiting the Earth at a height of this many kilometers above the Earth's surface. Okay, you're given the radius of the Earth. This is a second hint that the previous answer was wrong. The previous answer, the prefix is 10 to the power of 5. If you look at this prefix, power of 3 km, would be 10 to the power of 6. The radius of the satellite is less than the radius of the Earth. So the satellite is an underground satellite? Cannot be right. It has to be above the radius of the Earth. So this is how you can always check your answers. Okay. So here, you can see that now we give you the radius of this other satellite. So the GPS satellite, right, is not a geostationary satellite. It's a type where you can control with a remote or you can adjust the orbit one. Okay. So it orbits the Earth at a height this much above the Earth's surface. You're given the radius and use the answer to calculate, and the expression, this answer and this expression to calculate the period of the orbit. So this part, right, they're very nice. They give you the proportionality relationship, but you can actually tell the proportionality relationship from this equation, because you see 4 pi square and gm are constants. So from here you can tell that t square must be proportional to r cubed. Okay. So because of this, I can plug it in. All right. So t squared is proportional to r cubed. So I can put t1 over t2 squared, r1 over r2 cubed. Okay, sidebar mathematic time. In case you don't know why I write the fraction like that, it's because when you throw away the proportionality relationship, you will insert k, correct? Whenever you insert k, you can then put t1 r1 and t2 r2. And what happens when you divide both equations? You get t1 over t2 squared over r1 over r2 cubed. All right. So now you are looking for T2, you know R2, and this one is R1. So 24 hours over T2 would be R1 over R2. So here's a common mistake. This is the Earth's surface. You have to add from the Earth's center. So the Earth's radius plus above the Earth's surface, the total distance. So a lot of people, they will just put this height without adding the Earth's radius law. That's why, physics very hard law. Actually, it's because you are not used to the equation. Do more question, level up, get more EXP. Alright, anyway, you might be wondering, Miss, you never convert Why you no convert the 24? Well, number one, T2 can inherit the unit of 24 because this is ratio. Number two, there's no gravitational constant in the equation. If there's no gravitation constant, then you will not need to convert if you know what you're doing. But if you don't know what you're doing, you convert again. Anyway, this one is hours, so the unit. All right, so please be very careful whenever there's a physical constant like this one, whenever this calculation like that, you need to allocate some time, you convert. Okay, this one, SI conversion for 24 hours is not needed, and the reason why it's not needed is because you are using ratio. Let's move on to the next question. State Newton's law of gravitation. This statement is 2 marks. To score 2 out of 2, you have to have the idea of point mass. So gravitational attractive force between 2 point masses have to be 2 point masses. Is directly proportional to the product of their masses and inversely proportional to the square of their separation. So the hampelanga, the whole thing at the back, is 1 mark. The idea of 2 point masses is 1 mark. Okay? You might be thinking, Miss, I just write 2 point masses, I get 1 mark. Very nice, you get 0. You will not get the point mass mark if you don't write the relationship correctly. I don't set the rules. Because you write 2 point masses, it makes no sense. Okay? Anyway, here you have a distant star orbited by several planets. Each planet has a circular orbit. Big hint, giant hint, centripetal force. Okay? So right now, each planet orbits at a constant speed. Explain whether the planets are in equilibrium. This is a throwback to the previous chapter. Okay? because the direction of the velocity will change in a circular orbit, there has to be acceleration. If there's acceleration, it is not in equilibrium, because when you have acceleration, you have resultant force, and this resultant force is fondly known as centripetal force. Right now, you are given some data, okay, and you can see that the questions are fairly similar, okay. You are given the radius of an orbit of a planet R, okay, and the orbital period is T. The relationship between, so you give you a bunch of planets, and then they have a bunch of values of R and T. So the relationship between R and T is given by R cubed is proportional, is equal to KT square. Once again, you encounter the form R cubed is proportional to T square, which is similar to the one that you did before. Okay, there, T square is proportional to R cubed. It's the same thing. Anyway, this is page 32. Because there's a request for me to recite the number. My bad. Page 32. Okay, so let's go back to the question a bit. I want to talk a bit about this relationship. This is known as Kepler's third law. Miss, what is Kepler's first law, second law, third law? Okay, now, in the new SPM syllabus, the new Malaysian national syllabus, the Kepler's laws are being taught. So I'm thinking that maybe they want to send future you to a space planet. I don't know. But Kepler has 3 laws. The easiest one to understand is the larger the radius, the longer it will take for the satellite or the planet. Look, planet is a satellite for the sun. Moon is a satellite for a planet. You know that, right? Are you mind blown? Please don't be, okay? So Kepler's third law says that for a circular orbit, the larger the radius, the longer the period will be. And it's governed by this relationship, lah. R cubed is proportional to T square. You have proven it in the previous question. We will prove it again here. But the idea is there's 2 more laws, and then if you're interested, go and find out more about it. But it is not in our syllabus at the moment. Alright, so we shall continue. Okay, so show that the constant K is given by this expression. Well, we're going to start off the same. Gravitational force provides centripetal force. Whenever they ask you to show for circular orbit, this one always will work. So centripetal force will be equal to Fg. And I'll put mr omega square is gmm over r square. Cancel off the m. M here is the mass of the satellite once again. And I will have r cubed omega square is equal to gm. And I can substitute omega square as 2 pi over t. And then I notice, they use big R. Better follow them lah. Use big R. Please follow the question. Okay, so this will be gm over t over 2 pi square. Because the omega square, omega is 2 pi over t, bring over here, becomes t over 2 pi. Omega is 2 pi over t, bring over here, becomes t over 2 pi. So I will get this expression, gm over 4 pi square t square. So if you compare, r cubed will be proportional to t square. Whatever that is inside the bracket will now be your constant k. Okay, so we're comparing. R cubed is kt square ma. So from here, you can then say, by comparison, k will be equal to gm over 4 pi square. Okay, do not skip step. Alright, anyway, using the data and the expression for k, calculate the mass of the star. So we can use k is equal to r cubed over t square. And then you might be thinking, Miss, I got 3 numbers. Do I need to use all the numbers? The answer is yes. No, they give you 3 for what? Oh. So we do for planet C. Okay, so here is where I want to catch something first. R cubed over t square, you will take 9.6 times 10 to the power of 10 power 3, but you divide straight with 2.5 times 10 to the power of 11. This one no need to square. Ask me why? Because there's a square here. So many people go and square. And then wrong. So sad. Okay, I'll teach you how to catch yourself when it's wrong, but we shall continue first. Alright, so we continue. Our planet E, copy paste law. 4.0 times 10 to the power 11 divided by 1.8 times 10 to the power of 13. Okay, then we repeat again for the planet G. Normally I write like that, then I'll take out my calculator and press everything one go. Alright, so you will actually have 3 K values. Feels a bit like paper 3. Sure. Okay, so you have 3K values, and what do we do with them? Do we pick our favorite one? No, we find the average. But thank goodness, they are so symmetrical, you already know the average will be 3.55. If not, then you just add together and divide by 3. Okay, so K will be gm over 4 pi square. So if you want to find m, it will be 4 pi square times the average value of K divided by the gravitational constant. Ladies and gentlemen, boys and girls, this is a sun. Okay, a sun should be 10 to the power of 30 something kilogram. If you make a mistake and you square this K, this 2.5 times 10 to the power 11, you square when you're not supposed to square because the table gives you T square already, then you will think about it, your K value will be small. And then your mass will be small, SMOL. And the sun, to be called a sun, cannot be small. Okay, so your value of m will be very small, and you go like nani, and then you go and check your working, and then you correct it, and then you get full mark. Okay, can I give you my EXP lah, but you receive or not, I don't know. All right, so this is my comment. Always be familiar with roughly what kind of 10 to the power you will get for the question. If not, you won't even know whether you're correct or not. Okay, so I'm gonna continue. So you might be thinking, where is the 3 mark, right? 1 mark is for substitution, 1 mark for the final answer. And if you use more than 1K, you get the 3rd mark. So if you only use 1K, right, you
Here's
will
a
lose 1
fact
mark.
sim for us to play around with. Sim in simulation lah. Okay, very fun one. You must go try. Go to the video description link down there and try it out. Okay, it's a challenge to play with, but here's our little Earth zoom out. If I enable gravitational force, I want to see the arrow, okay? So yeah, that's our two equal magnitude opposite direction forces. Now, if I want this Earth to orbit around the sun nicely, there's some very neat balance that I need. Well, of course, you need some velocity to keep this Earth moving, okay? That's our tangential velocity. Let's click play and see what happens first. Okay, the path, see? Make it move faster. Okay, so now it's keeping a nice circle. The poor Earth here wants to go in a straight line. Newton's first law. And then this straight line, this tangential velocity is where it wants to go, but this sun is exerting a gravitational force on the Earth, trying to pulling it in. So it's kind of like perpetually falling towards the sun as it goes. Now let's be cheeky and play around with this. What if the Earth slow down a bit so I make this velocity smaller? What do you think is going to happen? Let's see what happens. Dun, 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 dun. The end of the Earth is near because it is going smaller and smaller. And wow, you see this arrow so big? Means the Earth is pulling, the sun is pulling this Earth into the sun. So it's going to burn. We are going to die. Then you go up again. Then you kind of go down again. Okay, so now we're at a very funny orbit. So anything can happen in the universe. Looks like we survive. Just that our orbit is a bit like an egg yolk now. See the egg yolk? Okay, so go play around with this thing. See if you can get the moon to orbit nicely around the Earth. Can you get an oval, elliptical orbit? How about a satellite? Okay, you all have these forces going. Oh, the satellite crashed. Never mind. Yeah, but that's the fat sim. Go try it out to better understand how gravitational force can be a centripetal force for things orbiting around a very large object, such as this one, such as this one. Okay, that's all.
Hey, I'm back. So based on just now, the observation that you can see, and please play with the sim. You can find the description for that in the link for that in the description down below. I would like to point out that in order for you to actually understand Kepler's laws, one of it is actually shown in the egg yolk shape orbit. Okay, Kepler's second law says that the area swept must be the same. So go and find it. I'm not going to spend some time on it because the video is already running a bit too long. But I would like to redirect your attention to this question. This is May-June 17 paper 4.1. Okay, and for this particular question, right, you will need to think about, because this question is a bit different. Okay, I didn't crop the page number, so you can find in the handouts lah. All right. Let me try to get the page number for you. All right, this is page 18 now. 1-8, page 18 in your notes. May, June 17, paper 4-1. Okay, we will continue. By the way, right, spend some time to think about what is actually happening in your circular orbit, okay? And I feel that the video is a bit fidgety, but we shall see. I shall continue first. Okay, so explain how a satellite may be in a circular orbit around the planet. Same explanation. It's just that now we are going to refer back to your centripetal force. Okay, so the gravitational force of attraction between the satellite and the planet provides the necessary centripetal force for circular motion. So right now you have the Earth and the Moon. Same thing again. You have the radius. Earth radius is r. Distance of Moon to the Earth is nr. The Earth has a density of rho. The Moon takes a time t to complete the period. Okay. Show that the mean density is given by this expression. So here is where students tend to panic. Density. How to find density? Why this proof so weird one? You come down first. You come down. Okay. Always start with the basic equation. Density is mass over volume. Okay. Just like when you start with gravitational force, you start with Newton's law of gravitation, Gmm over r squared. When you talk about centripetal force, you start with the basic one. Then you derive. That way it's easier. You can't memorize so many equations lah. Do not take it as a challenge. I'd rather you use the brain power to do something else. Alright? So here, this one can be a hint. Circular motion ma. So centripetal force will be equal to gravitational force. That's why they ask you to explain. Now here you have to be a bit careful because the radius of the circular orbit is nr. So instead of mr omega square, it should be mnr omega square. Okay, so the same thing with the separation, it will be nr square. Once again, we cancel off the m and we rearrange. You will get nr cubed multiplied by omega. I'll sub as 2 pi over t already. And then it's equal to general manager gm. Okay, so I think I can find the mass. If I can find the mass, I can substitute inside here. And if I can substitute inside here, then my work is done. So to find the mass, I will rearrange and I get 4 pi square over n cube r cube over gt square, being very careful. So mass over volume. Volume of a sphere is 4 over 3 pi r cube. Not n r cube, but Miss, why? Darling, it's the volume of this Earth, not the volume of the orbit. It's very weird, okay? So this nr is for the radius of the orbit, for FC. This nr is for the separation between the Moon and the Earth, okay? This r is for the radius of the Earth. So when you study last minute, you memorize equation and you don't know what the r stand for, this question will hyper confusion you and then you lose 4 marks lor. And then I would know you didn't study, didn't do work, okay? So anyway, we'll cancel and simplify. Okay, as long as the examiner is satisfied with your algebra, it looks legit, then can already lah. It is proven. Okay, 1 over 3 bring up becomes 3, proven. Okay, so where are the marks? 1 mark is when you substitute a correct expression for m into m over v lah, as density. Okay, the other mark is your FC is equal to FG and then suitable algebra, convincing algebra. 1 more mark. Okay, next. The radius of the Earth is given. The distance between the Earth and the center of the Moon, which is nr, is also given. Period t of the orbit of the Moon about the Earth is 27.3 days. So 27.3 days is your period, right? Now you can use this expression to calculate density. Even if you didn't prove or cannot prove or somewhere hang K, you can still use the density expression. Do not waste the bonus that they're giving you. So we're going to use this equation, but before that I need to find my n, which is nr over r. I'll take the radius of the orbit, divide by the radius of the Earth, and I'll get about 60.19. In the next lecture, we will prove this 60.19, but for now, we shall use it first. Okay, power 3. Just substitute in. Again, we have the constant, which means we will need to convert the period into hour. So 27.3 days, 24 hours, 1 day, 3600 seconds. So I'll press my calculator and then I'll get the value 5.54 times 10 to the power of 3, but sometimes they can ask you to deduce whether this is a rock planet or a gas planet. So this is a rocky planet. How do I know? Density is bigger than the density of water. So it has to be rock law. If you get a density that is less than 1000, then it has to be a gaseous planet law, like gas, like the big planets. Okay. Anyway, that's all for this video. And the important thing here is to know what is Newton's law of gravitation. It is the attraction between 2-point masses, number one. Number two, this attraction between 2-point masses can contribute to centripetal forces. So to test your understanding of this, I would suggest you do the work supplied at the end of this lecture given by your lecturer. I'll see you in the next video. Goodbye.